Unit 3.1 is all about data structures. So it's looking at how we use different kinds of data structures, how we manipulate and operate them. The objectives in this case are all quite bland because what we need to do is get into each data structure and see how it works. Let's start with arrays. Arrays, on the whole, need to have the same data type. Arrays tend to be static. They are a fixed size and they can't be changed while the program runs. They can be multi-dimensional, which we'll have a look at in a second, and is part of what we call a random access data structure, in that I can access any element of the array as quickly as any other. A one-dimensional array, as on the left then, just looks like a list, and you can access elements based on zero indexing. So if I wanted to access this item that says maths, I'd be looking at the subject array and in square brackets tell me which index I'm looking at, which is number 1. So that must be the row. In a two-dimensional array here, if I want to access Mrs. James as content, I'd be using two square brackets, the first to illustrate the row, the second the column. So in this case it would be row 2, column 1. And this is different from how we do it everywhere else, and that is mainly because this isn't a grid, this is an array of arrays. A three-dimensional array then, where we take that a bit further and we have different tables. The way we access the green table's content A21 would be by saying the table index 2, row index 0, column index 1. And of course we can extend the dimensions of that array more than that, but it's only 3 dimensions that we need to know about for A level. Stacks are a different kind of data structure. They're a last in, first out data structure, so meaning that the last thing you put in is the first thing that comes out when you access it. It looks literally like a stack of items, and it's very computationally simple. It's also dynamic, it can change size, so it's a really useful data structure. And it looks like this. We've got a pointer to the top and the bottom, and the idea is, as we add a new element, in this case I'm adding gaming to my list of things I want to do, it goes on the top. And when I want to take an element off the stack, the only place I can take it from is the top, so gaming comes off. Now that probably looks like your own revision schedule, doesn't it? That other things take priority above revision. Stacks are not ideal data structures because we can't get to the first element in there very easily. A queue then is a first in, first out data structure where we can get to the first element quite easily. The first element in is the first element that is accessed and processed. It looks like a literal queue as if you were in a shop, and it must keep track of the front and back of the queue. We do that with pointers. It's also a dynamic data structure, so it can change in size. Here's our example with the same sort of list as before, a list of things we need to do. If we add an item to the queue, it goes in the back and the back pointer adjusts to reflect that. And then when I want to take something from the queue, I take from the front. So my revision is prioritized in this case. A linked list is a very dynamic and powerful data structure. It's basically an array, but we have 2 elements. We have the data and a pointer to the next item. That means in order to read the data structure in the correct order, we must traverse it, we must move through it. And if items are added or removed, we need to update the pointers, but it is the most dynamic of data structures. Here's an example with a simplified example at the top, on the bottom right, how that would look as an array. You'll see that we've got cooking, homework, and revision. They're the 3 items that we've got in our list. They're in a different order, you'll see, in the array itself, but look where the pointers are. We start with cooking. It's got a pointer to row 0, then homework, a pointer to row 1, a pointer to row 2 for revision, and then we're done there. If we want to add an item to the list, like gaming, it would go at the bottom of the array, and all we need to do is just the pointers. We'd need to point cooking at gaming, and we do that, and then we need to point gaming at homework. And we do that simply by changing the pointers in the table. Now, if we want to remove an item like homework, what we need to do is remove all pointers to it. So you'll see that gaming points to homework. So we need to update that pointer so it points to revision instead. Then we've got a linked list. Notice the item doesn't necessarily get deleted from the array. It can get erased and blanked out, but it doesn't need to be. The linked list is still perfectly fine and works accurately in this case. Trees, or binary trees in particular, are one of the most beautiful of the data structures we've got. They're built of nodes and branches. Each node has a maximum of 2 branches, one to the left and one to the right, thus a binary tree, and it's extremely dynamic, and as part of the creation process you automatically sort it. Now the thing to remember about trees is there are many different ways of traversing or travelling across the tree, and we need to know at least 3 of them. Here's an example of a binary tree. If we're going to insert data, what we do is we start at the root node, which is the topmost node. If the data is less than it, it goes to the left. If it's greater than it, it goes to the right. And we traverse the tree until there's a space in the branch where we can place it. So for instance, to add Lorna, we look at John and we say, okay, Lorna is greater than John. It's alphabetically to the right. With Norma then, we'll say that, well, the L is before the N, so that needs to go to the left. There's an item there already. So Kieran, Lorna goes to the right of that. L is greater than K, so goes to the right. How about deleting an item then? Well, if we take this first example, if we want to delete Alex, well, there are no child branches that we need to deal with, so we can just simply remove it, and it disappears. If we want to remove Barbara with only one child branch, what we do is we delete Barbara, and we change the branch to connect to the item directly above it. What happens though in the most complex sets if a particular node has two branches? Well, first of all, we identify which is the leftmost of its nodes. And what we do then is remove the item and replace it with its leftmost node. This will keep the sorting mostly intact. So how about traversing this tree structure then? Well, we've got pre-order traversal, and it's where we go from the root node, we record the result of each node we visit, and we go from the leftmost side first. So we start with John, and we write that down. We go left first, we got Barbara, we write that down. We go left again, we got Alex, we write it down. At this point, we've exhausted the left branches. So what we need to do is have a look at the right. That gives us Caris. We've exhausted those branches completely. We go back all the way up to our root node, to John, and now we can go right for the first time. Well, we encounter Norma, so she goes down. Then we go left again because we can, and we put Kieran down. We've exhausted that branch, so we come back up and go right, and we look at Xavier. And then we've exhausted all the branches, and the tree is completely red. That's pre-order traversal. Let's have a look at a different one. In order traversal then is where we go left and then right again as before, but in this case we only write down the item as we reach a node with no children. So in this case we start with John, it has children, so we go left. It's got Barbara, we go left. It's got Alex there. That node has no children, so we write it down. Now we've exhausted the left hand side, so we go to the right hand side, and as we do that we write down the nodes that we pass. So we pass Barbara. We go in then, Caris, the left-hand side, once we've got John then is totally exhausted. We go to the right again and we go to the most terminal point of the left-hand connection, which is Kieran, then Norma as we traverse that, then Xavier, and our tree is done once again. The final kind of tree traversal is post-order traversal, which is where we're going down the root node, leftmost until there are no more children, then read the rightmost. So we start off with John, Barbara, and Alex. There are no more children, so we get Alex. We go to the right, we get Caris. We pop back up and get Barbara. We go to the right then and straight to the left. We exhaust the leftmost choice. Once we've done that, we can pick up Xavier, then Norma, then John. The final data structure you need to know about is hash tables. I'm not going to talk about that here because I've covered it in ridiculous detail in the 4.4 playlist, Organization of Data. Go have a look at that if you want a bit more detail on hash tables.